Okay, hi, Assalamualaikum. My name is Muhammad Lufi Akmal and I am one of the students in class A. So, today I'll be presenting my topic of choice, which is chapter 3 induction motor. So, first of all, what is an induction motor? So, induction motor, also known as a synchronous motor, is a commonly used AC electric motor. In an induction motor, the electric current in the rotor needed to produce torque is obtained via electromagnetic induction from the rotating magnetic field of the stator winding. The rotor the rotor of an induction motor can be squirrel cage rotor or wound type rotor. Induction motors are referred to as asynchronous motors because they operate at a speed less than their synchronous speed. So, let's go to the next slide. So, what is synchronous speed? Synchronous speed is the speed of rotation of the magnetic field in a rotary machine, and it depends upon the frequency and number of poles of the machine. The induction motor always runs at speed less than its synchronous speed. The rotating magnetic field produced in the stator will create flux in the rotor, hence causing the rotor to rotate. Due to the lag between the flux current in the rotor and the flux current in the stator, the rotor will never reach its rotating magnetic field speed. In example, the synchronous speed. There are basically two types of induction motor. The types of induction motor depend upon the input supply. There are single-phase induction motors and three-phase induction motors. Single-phase induction motors are not a self-starting motor, and a three-phase induction motor are a self-starting motor. So in this chapter, we will focus on a three-phase induction motor. So the construction. Stator, as its name indicates, stator is a stationary part of the induction motor. A stator winding is placed in the stator of induction motor and the three-phase supply is given to it. Rotor. Rotor is a rotating part of induction motor. The rotor is connected to the mechanical load through the shaft. So, the production of rotating magnetic field. When a three-phase supply is fed to the stator winding of the three-phase induction motor, a rotating magnetic field RMF is produced. The magnetic field is such that its poles do not remain in a fixed position on the stator but go on shifting their position around the stator. For this reason, it is known as rotating magnetic field, or RMF. Mathematically, it can be shown that the magnetic of the rotating magnetic field is constant and is equal to 1.5 times of the maximum flux due to the current in any phase. The speed of the rotating magnetic field is known as synchronous speed. The value of synchronous speed depends upon the number of poles and the stator on the stator and the supply frequency. Hence, the formula is created. Ns is equals to 120 times frequency supply divided by poles. So, the advantages and disadvantages of the induction motor. So, the advantage is the construction is simple. The stator construction is similar in both synchronous and induction motor maintenance, and the maintenance is low. The working of motor is independent of environmental condition because induction motor is robust and mechanically strong and no spark due to absence of brushes and can be operated in any environment condition. It is high efficient with full load efficiency varying from 85 to 97%. It also has a high starting torque and good speed regulation and also a reasonable overload capacity. But the disadvantage is that during light load condition, power factor drops very low due to large magnetizing current drawn to overcome reluctance due to air gap between stator and rotor. It have a high input surge current which referred as magnetizing inrush current that causes a reduction in voltage at the starting of the motor. It also cannot be used for application with high starting torque due to poor starting torque. The speed control is difficult to attain. So, in this chapter, we we are introduced with per phase and actual circuit. So per phase and actual circuit is introduced is because it is a method for accurate estimation of the equivalent circuit parameters of induction motors at different operating regimes from a set of measurement data containing the rotor cage temperature and rotor resistance. The actual circuit obtained from the per phase circuit. So to simplify the circuit, we create an approximate equivalent circuit to allow students or anyone to construct and to calculate the value easier. So from the slide, these are the parameters from the actual circuit and the approximate circuit. So I phase is equals to I2 plus I node. I node is the current that go through the RC. The RC and the inductor. And R air gap, which is the resistance of the air gap, is obtained from the formula of R2 over S. S is slip. Slip is obtained by the formula of the speed of synchronous speed. And R2 is the R prime R, which is the resistance of the rotor. So next we are introduced to power flow diagram. So power flow diagram have these parameters, which is power in, power stator copper loss, power core loss, power air gap, power rotor copper loss, power conversion, and power losses, and lastly power out. This power flow diagram is to show where the power is lost. So for the P in the calculation is depends on the type of connection. So if in star connection, we have calculation based on star connection, which is 3 V phase I phase cos theta. However, if the connection is in delta, we need to change it to if the connection is in delta, if the connection is in both delta or star, we can choose either to calculate using phase or line. So in order to calculate in line, we have to substitute the 3 value with the set 3 value, and then the V phase and I phase in line, voltage line and current line. The voltage line and current line depends on the type of connection. If delta, the V phase is same to V line. If in star, I phase is same with I line. So the other connection is a basic power formula, which is derived from P equals to IV, which is I square R. But because this is a 3-phase system, we need to multiply by 3. For the power conversion, the formula given is power air gap times 1 minus slip. And the power losses is the sum of total losses that the motor provide. Lastly, we have the power out, which is the formula of power conversion minus with power losses. So based on this video, this is the calculation that is needed to rule out all the data that we need, such as power flow diagram and the value of current, to find the efficiency, which is efficiency is equals to P out over P in. So this is the video. As you can see, first we have to draw the approximate equivalent circuit. Note that this is the important parameters that we need to rule out first. So slip, if not given, we have to find slip, which is ns minus nr over ns. Next, we have to see whether either they give RC or not, because if RC isn't given, it will affect the power flow diagram. Later I will explain. So as you can see, after we draw the approximate equivalent circle, we need to find the RA gap. So RA gap is obtained by this formula, R roto divided by slip. Okay, next, with that information, we have to find the current that flows through I2 in order to complete to find the I phase or I line. We need to find I2 first, then we need to find I node. So the first one, we need to see either the connection is in star or delta. So as you can see, first we total up all the value of resistance in the I2 flows in order for us to calculate easier. So next, we have to rule out either it is in delta or star connection. So in this case, it is in star connection. So if in star connection, let's say the voltage given here is we need to divide it by cert3 in order to make it into phase. It is not required for us to change, but it is easier for us to calculate if it's in phase. So to find the value of I2, it uses the simple electrical formula that everyone knows, which is V equals to IR. So we can derive by using I equals to V over R. So after finding I2 and I node, we can find the value of I phase. So in this case, which is star connection, I phase is equals to I line, so we don't need to change anything for the current. Okay, next, as you can see, we first draw the power flow diagram. So as the slide before, power flow diagram consists of parameters such as power rotor copper loss, first power in, second power stator copper loss, and then power core, and then we separate the part with power air gap, and then follow up with power rotor copper loss, power conversion, and power losses, and finally power output. Okay, the power core is neglected because in this case there are no resistance of RC that is given in the question. So we need to draw a new power flow diagram. As you can see, this is the new power flow diagram, and based on the power flow diagram, we can rule out all the value that we need, such as P in, especially for power conversion and power out. To find P in, it uses a simple it uses the basic formula, which is 3V phase I phase cos theta. Cos theta is the power factor. In order to find the power factor, we need to find the angle. So the angle that is given, which is delta V, is equal to 0 minus negative value of the angle that we obtain from I2. So as you can see, we are finding all the power value for each parameters to find the efficiency. So the important part is the P out over P in, because that is the efficiency. So as you can see here, it is high efficient, which is 93%. So the efficiency is in percentage. So that's all from me. So the important part of this chapter is that we know what is an induction motor and why it is important for us to know the calculation, so that we can know where the power losses, and we can calculate the efficiency of the induction motor itself. So this chapter is heavily implied to the calculation part. So that's why I explain more on the calculation part instead of theoretical part. But I covered all that is needed to know for the theoretical part. So that's all from me. Thank you very much.